Recording. Okay, so as I said before, thank you all for joining today's seminar. I know that you must be tired from the previous one, but once again, thank you. So today we are going to have with us Dr. Stefano Gabici or Gabici?
Gabici.
Gabici. So Stefano is a theoretical astrophysicist with expertise in the physics of cosmic rays, including cosmic ray acceleration and propagation. He has done lots of work in modeling and theoretically interpreting the cosmic ray sources in our galaxy. He graduated from the University of Firenze in 2004. And since then, he has received several prestigious postdoctoral fellowships, like the Humboldt Fellowship and the Marie Curie Fellowship. And since 2009, he has been a researcher at the Astroparticle and Cosmology Center of the University of Paris, and also is a researcher at the associated CNRS, which is an institute, the French National Institute. He's also a member of various collaborations, including the HES collaboration and the CTA consortium. And also he's the coordinator of the High Energy Astrophysics group here at APESE. So it's a great pleasure that Stefano will be giving the astrophysics seminar today. And the floor is yours, Stefano.
Thanks a lot, Maria, for the invitation. So I will talk today about low energy cosmic rays in the interstellar medium. So before starting, just let me allow for some self-advertisement. I very recently wrote a review on A&A reviews on this topic. So if you are interested in this topic, you may want to check this. So let's start from a question. Why is it difficult to study cosmic rays? And why it is even more difficult to study low energy cosmic rays? So we can start with the basics. This is the beginning of the book by Tom Geiser, Cosmic Rays and Particle Physics, which is a classic book in the field. And basically, if you read the first lines of this book, you see that cosmic rays are high energy particles that hit the Earth's atmosphere from outside. And if you look at the composition of these particles, quite roughly, it looks like solar or cosmic composition, because you have 90% of protons, 9% are helium nuclei, and the rest are heavier nuclei. And of course, people working in cosmic ray physics want to answer the questions, where are these particles from and how they are accelerated to these high energies? And of course, the answer to this question is still not fully solved. Now, the main problem in studying cosmic rays is that they are charged particles, they are atomic nuclei, and so they are deflected by magnetic field. So while you can do astronomy with photons, you cannot do it with cosmic rays. So if you look the arrival direction of a cosmic ray, well, this does not point to the direction of the source. And that's why we still don't know where are the sources of these particles. Then let's go back to the book by Geiser. What we know is that these particles come from outside of the solar system, but most of them, the vast majority of them, comes from within our galaxy. And there is, at low energies, there is a clear anti-correlation with solar activity. So it means that if this is the spectrum of cosmic rays measured, each color corresponds to a different epoch, and the blue corresponds to a minimum in solar activity, and the red to a maximum of solar activity. So it means that there is a clear correlation between the fluxia at low energies and the solar activity. And the reason is that there is a solar wind which is pushing back low energy particles. High energy particles are not affected because they can diffuse fast, and they basically they do not feel the presence of the solar wind. Okay, so and this modulation, we call solar modulation, it's important below, let's say, 20 GeV. Good, so the study of energy cosmic rays is difficult because it is affected by the presence of the sun. So we do not measure the real spectrum of cosmic rays outside of the solar system, but we measure something modulated by solar activity. So in 1977, when I was 1 year old, the Voyager probes were launched, Voyager 1 and Voyager 2, and these were amazing, amazing probes that are still working, and now they are at 162 and 135 astronomical units from us. And they have on board cosmic ray detectors, and these cosmic ray detectors are still working. So when you change your mobile phone every year, think about this, that these instruments are working since 46 years, and they are still sending us data on the cosmic rays. And this was a very real breakthrough, because here you see the rate of cosmic rays. This is Voyager 1. The rate of cosmic rays detected by the cosmic ray detector as a function of time. And you see clearly that at the beginning, you see these oscillations, which have a period of 11 years. So this is clearly the solar cycle. And then as the probes went farther and farther away from the Earth, at some point, the Voyager 1 crossed the wind termination shock. And you see that here the oscillations are less pronounced. And then at some point, they reached heliopause. And then look at the count rate, which is zoomed in here. It becomes very, very, very stable. So the interpretation of this is now Voyager probes are outside of the influence of the solar wind. So they cross the heliopause. And so what they measure now is the pristine spectrum of cosmic rays in the local interstellar medium. Okay, this I can skip. It's just another evidence for the same thing. So now these white data points here are the points collected by Voyager 1 and 2. You see there is very good agreement between the two instruments. And so this is not changing with time. So this is the real spectrum of the cosmic rays in the interstellar medium, or something extremely close to it. Because there was some discussion if there is still some residual modulation, but as the variations are very small, if there is some residual modulation, it must be small. So we are very close to what we expect to see in the interstellar medium. Then, of course, Voyager measures also helium and heavier nuclei, and also electrons. This is a spectrum of electrons. And you see that if you plot the intensity of cosmic rays, the intensity is how many particles cross a unit surface per unit time, per unit steradian, and per unit energy. If you plot protons and electrons, you see that at high energies, proton dominates, and at low energies, electron dominates. And this is important for what we will see in the following. And you also note that these Voyager data are these low energy points here in the MEV domain. And here there are also, I think these are AMS data. And AMS data start from, let's say, GV or whatever. And you see that there is a gap in between. And so the shape of the cosmic ray spectrum here is not known from direct measurements. Can we do something to fill this gap? Yes, because, for example, for protons, cosmic ray protons can interact with interstellar matter in proton-proton interactions, and these interactions can produce neutral pions that decay into gamma rays. So with gamma ray astronomy, we can try to fill the gap, because if you want to produce a pion, so you produce a new particle, so you need a minimum energy of the cosmic ray. There is a threshold, and this threshold is about 280 MeV, which is here. And so you see that Voyager data are all almost below this threshold. And these particles here, from which we don't have a clear measurement of the spectrum in interstellar medium, they can produce gamma rays. So now if you take our galaxy disk, so the gas is distributed in the disk, we are here at the edge of the disk. If we look at high latitude, we see the gamma ray emission from cosmic rays which are close to us. If you look along the disk, you see all the cosmic rays interacting with matter along the entire galaxy. But if you look at high latitude, you look at the local one. So we can define a limit in galactic latitude so that we see the interaction of cosmic rays in the local kiloparsec, let's say. And so if you do this, this is the spectrum of gamma rays that you observe, and we know that these gamma rays are mostly due to this proton-proton interaction. And in this way, we can reconstruct the spectrum of cosmic rays in these gap regions. And there is some discussion, it may be there is a slight mismatch with respect to Voyager, but I didn't quote it here, but there are recent papers by the group of Philip Mersch in Aachen that claim that maybe this offset is not even there. So, but in any case, we can measure the spectrum in an indirect way in the region where you do not have direct measurement. And you can do the same with electrons, but with time, of course, not with gamma ray observation, but with radio observation, because you see in this gap region here, these electrons emit synchrotron in the radio. And so again, if you observe synchrotron diffuse emission at high latitude, you can fill this gap here. And so we have the spectrum of protons and electrons in the local interstellar medium at all energies. And then we can compute some quantities. This is the flux. So is a square number of particles per square centimeters per second. So if you have a surface, is the number of particles flowing across this surface per unit time. You see that for protons and nuclei, this quantity peaks at, let's say, few hundreds of MeVs. But for electrons, this quantity peaks somewhere outside of the plot. And Voyager measured the electron down to 3 MeV, so down to here. So we don't know where the peak of this is. Okay? If we integrate the nuclei, we get a density, a particle density of cosmic rays of this order, 10 to minus 9, 10 to minus 10 particles per cubic centimeter. Now let's go to this, the bottom plot, which is the energy density of this part, the spectral energy distribution of this particle. So E squared and E, so electron volt per cubic centimeter. And you see that this quantity, all species, including electrons, peaks at around GeV. Okay? So the energy density is something well defined. The flux, not, because we don't know where electron peaks. Now, if we take the energy density of all these particles, it's about 1 electron volt per cubic centimeter. And this is very important because now let's compare the number density of cosmic ray with the number density of protons in the interstellar medium. And you see there is a huge difference, so the 10 orders of magnitude difference. While the energy density, 1 eV per cubic centimeter, is of the same order of the magnetic, thermal, and turbulent energy in the ISM. So you have very, very, very few particles with a lot of energy. And so the energy density is comparable to the other components of the interstellar medium. So if you want to answer the question, what is the origin of cosmic rays, you need to go to the lower plot, because we want sources capable of accelerating, of converting a lot of energy in cosmic rays, because it's an important component of the interstellar medium. The upper plot is important if you want to answer the question, what do cosmic rays do on the interstellar medium? Because this flux is determining the ionization of the interstellar medium, is determining the heating, and also the chemistry. Basically, it's the rate at which cosmic rays bombard the interstellar medium. Okay? Okay. So that's it. So in other words, if I can go back a second, cosmic ray physicists very often think about this, and astronomers doing astrochemistry and molecular clouds, they think about this because they want to know what is the impact. Okay, I'm a bit oversimplifying, but we will discuss later these two aspects more in detail. Okay, so far I talked only about local cosmic rays, so measured just at the Earth or just outside of the heliosphere or in the inner kiloparsec if you use indirect observation. What about faraway cosmic rays? So faraway cosmic rays, we know that there are cosmic rays far away because if we look at the sky in the GeV domain, we see this. This is the Fermi all-sky map, and the most important gamma ray GeV source in the sky is this, the galactic disk. And this emission is mainly due to interaction of cosmic rays with interstellar gas. So it means that cosmic rays are everywhere in the disk, because otherwise we wouldn't see this pronounced, very pronounced disk everywhere in the sky. And so cosmic rays fill the entire galaxy. And again, there is a complementarity, because when we observe, so Voyager observed low energy local cosmic rays, and with Fermi we can observe high energy and remote cosmic rays. Okay. And now, before entering to the main topic of this talk, briefly, let's see briefly what we believe now about the origin of cosmic rays. The origin of cosmic rays, a very important thing is to look at their composition. So basically, this is the atomic number, and this is the abundance, and the black is the abundance in the solar system, and the green is the abundance in cosmic rays. So these abundances are quite similar, with some really huge exceptions, like lithium beryllium boron. Remember, beryllium, there is 1 million times more abundant in cosmic rays than in the cosmic abundances. And also some sub-iron element that very like 1,000 times more abundant in cosmic rays. What is this? This is because these elements in cosmic rays are produced in spallation. So you take, for example, here you take carbon. So you take carbon in cosmic rays. When carbon interacts with interstellar matter, it does spallation. So basically it fragments. And after this process, it is fragmented into lighter nuclei, so among which you have lithium, beryllium, boron. And so if you want to explain the difference between this amount of lithium, beryllium, boron and this one, you need to invoke a grammage. So this carbon, neon, oxygen, cosmic rays, they have to cross a given amount of matter sufficient to create this amount of lithium, beryllium, boron. Okay? And if you know how much matter these cosmic rays need to cross, you also know how much time they need to be confined to the disk, because you know the density of the disk, and so you know that after a given time in the disk, they will accumulate enough grammage to produce lithium, beryllium, boron. So basically, you get some time scale of confinement, which means that if you know from gamma ray observation, you know how much cosmic rays you have everywhere in the disk. From lithium, beryllium, boron, you know how long cosmic rays stay confined in the disk. If you divide the two, you get the power of cosmic rays in the galaxy. And this is 10 to 41 Hz per second. Okay? The kinetic energy injected in the disk by supernova is 10 to 42 Hz per second. And that's why people, since a very long time, start to say, okay, supernova explosions can provide the energy to explain cosmic rays if 10% of the mechanical energy is converted somehow into cosmic rays. Okay? And now we believe that the shock waves which originate in the remnants of supernova explosions can accelerate particles and produce the cosmic rays that we observe at the Earth. This is the mainstream, let's say, in cosmic ray community. This scenario is not, as we will see at the end of the talk, is not proven. And in fact, now there are some problems that are still there, and probably we need to modify a bit this scenario. Okay. So how do cosmic rays impact on the galaxy system? So there are, again, two ways. One is through their pressure. So for example, we know that cosmic rays most likely play a role in launching the galactic wind. And then through their pressure, they also can excite MHD turbulence in the galaxy. Then if we consider particle interactions, so here these two things correspond to the upper and lower plot a few slides ago. So the cosmic ray pressure and cosmic ray flux, basically the bombardment rate. So the interaction with spallation, you produce lithium, beryllium, boron. All beryllium and boron in the universe has been produced by cosmic rays, and also a significant fraction of lithium. Lithium also the Big Bang did something, and stars do a little bit. And then they also ionize the molecular clouds, and so they determine the coupling between the gas and the magnetic field in clouds, and so they affect stellar and planetary formation. And then they ionize molecular clouds, and so you know that in chemistry you need the ion-neutral reaction, which are much faster than neutral reactions. So basically, cosmic rays drive interstellar chemistry in clouds. And then, of course, when they ionize the gas, they also heat the gas, and so they are a source of heating in molecular clouds. So this is to tell you that the importance of cosmic rays goes beyond the problem of their origin. I mean, cosmic ray physicists want to know the origin, but there are many other things that are important in astrophysics and are connected to cosmic rays. Okay, so now let's go to the main, to the core of this presentation. I will now try to answer the question how well we know the spatial distribution of cosmic rays in the galaxy. To do so, we need molecular clouds. So molecular clouds are massive clouds of gas in the interstellar medium, and these clouds are embedded in a sea of cosmic rays, because we know from gamma ray observation that cosmic rays are everywhere. So cosmic rays will bombard the cloud, produce neutral pions that will decay into gamma rays, and so molecular clouds are expected to be gamma ray sources. This is very interesting because if you have now a cosmic ray source is located next to a molecular cloud, well, you would expect the cloud to have a larger gamma ray flux, because you have a lot of cosmic rays escaping from the source, they bombard the cloud, and so you expect the gamma ray flux to be larger. And that's why molecular clouds can be used to probe the intensity of high-energy cosmic rays in different locations in the galaxy. Now, the disk of the galaxy is also filled with UV radiation, ionizing radiation. But this radiation cannot penetrate molecular clouds because of their large gas column density. And so it means that the only ionizing agent of molecular cloud cores, of the inner region of molecular clouds, are cosmic rays, because photons are absorbed. So molecular clouds are very important because at high energy, they tell us how many cosmic rays we have in the region, because we see their gamma ray emission. But at low energy, they are a filter of UV radiation. And so if you can measure the ionization rate in these clouds, this is due to cosmic rays. And so we can infer something about the low energy cosmic rays. So molecular clouds are useful both for low and high energy cosmic rays. Okay, and in fact, we can measure the ionization rate of molecular clouds through observation of lines in the infrared or in the millimeter domain. We can observe lines from some molecules that can tell us which is the ionization rate. We will see this in a moment. So for high energy cosmic rays, the problem is very simple. You have a cloud with a given mass that emits gamma rays, and then the cloud is at some distance, and you observe the cloud with the Fermi, for example, satellite in the GV domain. And the gamma ray emission from the cloud is simply the density of cosmic rays in the cloud times the density of the target, because you know this proton-proton interaction, one cosmic ray hits a proton in the interstellar medium. Then you multiply by the cross-section to have the proton-proton interaction, and you multiply by the volume. So basically, gas times volume is the mass. So the gamma ray luminosity is cosmic ray density times mass of the cloud. What you observe is the flux, so is the luminosity divided distance squared. And so this is proportional to density of cosmic rays mass d squared. This is the observable. This you can measure. You take Fermi and you measure the gamma ray flux, and you take, for example, CO data, and you measure the mass of the cloud and this distance through the rotation curve. And so if you measure all these quantities, you can extract the density of cosmic rays. And this is why very often we say that molecular clouds can be used as cosmic ray barometers, because we know how many cosmic rays are there. Good. Now, look now only the upper panel of this figure. This is a collection of data from many molecular clouds where this game was played. So gamma ray data were taken, the mass of the cloud was known, the distance was known, and so the intensity of cosmic rays here is, for example, at 30 GeV, is plotted as a function of the galactocentric distance. Okay. Now look the y-axis of the plot. The y-axis is in linear scale. It's not log scale, it's linear scale. So it means that there are variations in the cosmic ray intensity in the disk, but is within a factor of 2, 3. It's not dramatic variations. Okay, so keep this in mind, because now we move to low energy cosmic rays. So low energy cosmic rays, to determine how many low energy cosmic rays are in clouds, we need to do a bit of astrochemistry. So basically what the process, a cosmic ray hits a molecular hydrogen in the molecular cloud and ionizes it. And this happens at a rate which is called the cosmic ray ionization intensity times the ionization cross-section. Okay. Then once you, and so this is basically the rate at which you ionize. And then once you have H2 plus, there is a very fast reaction, which is H2 plus with H2, which creates the H3 plus. And this is extremely fast. It's much faster than the cosmic ray ionization rate. So we can say that production rate of H3 plus is basically the cosmic ray ionization rate times the density of H2. Then H3 plus is destroyed in dissociative recombination. So you get an electron and your H3 plus becomes HHH or H blue A's. And we know the rate at which this happens because this coefficient of this reaction has been measured in laboratory experiments. So now we know it with quite reasonable accuracy. And so from this very simple chemical network, we can try to infer the cosmic ray ionization rate. Before proceeding to show how we do it, we should remember that this is an integral quantity. We take the spectrum of cosmic rays and we integrate it. So in gamma ray astronomy, we measure spectra. So we can extract not only how many cosmic rays are there, but also the spectral distribution. With the ionization rate, we only measure an integral quantity. So we lose all the information on the spectrum. So we just know a kind of an integral weighted on the cross-section of how many cosmic rays we have there. Okay, so if you equate the production and destruction rate of H3 plus, you get this simple equation. You see that the amount of H3 plus that you have in your cloud is proportional to the cosmic ray ionization rate, to the density of the cloud that you can measure, and the density of free electrons in the cloud, which can also be measured. Of course, astronomers work with column density and not with density, so you need to introduce the length of your cloud along the line of sight if you want to pass from density to column densities. And you can manipulate this equation and obtain this expression for the cosmic ray ionization rate times the length of the cloud along the line of sight. Now, this is measured in the lab, is the rate coefficient for the distraction of H3 plus. The density of free electrons in clouds can be measured in the UV. For example, the UV lines can tell you both the column density of H2 and the number of free electrons, because in diffuse clouds, basically the number of free electrons is dominated by the ionization of carbon, and carbon has a UV emission line that you can measure. So if you measure all this, then you need to measure the H3 plus abundance and you know the ionization rate. The H3 plus is observed in absorption in the infrared spectrum of stars which are located behind the molecular cloud. So from observation, we can measure everything, and we obtain in diffuse clouds a rate of ionization of the order of 10 to minus 15, let's say. We will see in the following more data. But this was a big surprise. This was observed for the data per se diffuse cloud. This was a big surprise because based on cosmic ray observation, we would expect something much smaller. Okay. Okay. Now, this works for diffuse clouds because the H3 plus, you can measure it if you have a star behind the cloud and you measure in the absorption spectrum. If you have dense clouds with large column densities, then it's impossible to play this game because the star is completely absorbed and you cannot get a spectrum. So for dense clouds, you need to go to emission lines. And this can be done, okay, to make a long story shorter, chemistry is a bit more complicated because you need networks of more reactions, but there are molecules like HCO plus and DCO plus, which can trace the amount of low energy cosmic rays. The idea is simple. In dense clouds are more neutral, so you have less free electrons because they are better shielded by cosmic rays and radiation. And if you have less free electrons, you do not destroy H3 plus in dissociative recombination because you don't have enough electrons, but you destroy H3 plus in interaction with CO, which is the second most abundant molecule in clouds after H2. And so H3 plus CO gives HCO plus. Okay, and DCO is a deuterated brother of HCO plus. And so this ratio helps in determining the cosmic ray ionization rate. Okay, And this is your emission line for DCO plus and HCO plus. And there are some pioneer papers in the 90s by Paola Caselli and other people that show that this line ratio can be used to infer the cosmic ray ionization rate in clouds. Now, this plot is a collection of many observations of many different clouds. The cosmic ray ionization rate in many clouds is a function of the cloud column density. Okay. Different colors refers to different traces, but there are many molecules which are used. And so what is this plot telling us? First of all, dense clouds, so large column density, tend to have an ionization rate which is smaller than diffuse clouds. And this is one first important thing. If you take now the spectrum of cosmic rays measured by Voyager, and you assume that this spectrum is characteristic of the entire galaxy, and you integrate the ionization rate, and this is very important to go back. So you remember this plot here? We go back to the very beginning of the talk. For protons, what determines interaction is the flux. So for protons, this is well picked at MeV, and Voyager measures this. So we can measure the ionization rate from local cosmic rays with very good accuracy, because we need to know the spectrum here, and we know it. For electrons, no, that's important. So now go back, sorry, this is a bit annoying. Where are we? Here. So if we integrate the Voyager spectrum weighted with the ionization cross-section, you get this yellow line here. So that's not good. I mean, for dense clouds, it would be sufficient, but not for diffuse clouds. If you take Voyager electrons and you compute the ionization rate down to the lowest energy Voyager point, you got this. So also is not enough. But you remember, for electrons, you don't know where the spectrum ends. I mean, you don't know where the spectrum peaks. And so if you extrapolate down to 3 keV, you can reach the level of diffuse clouds. Okay? Another remarkable thing is that, see here, there seems not to be a trend, even if the column density changes a lot. So this is interesting. And then at some point it goes down. And this I think we don't understand fully yet. Okay, so can we say that this ionization is due to electrons and the electron spectrum has to be extrapolated down to keV? The answer is no. Because cosmic rays, when they penetrate clouds, they lose energy due to ionization losses. And this is a plot of ionization losses for protons and electrons as a function of the particle energy. And here, instead of plotting the lost time, I plotted the column density that the particle needs to cross to lose its energy. So this is the column density that you need to cross to lose energy. And here I put very, very roughly the division between diffuse and dense clouds. So you see that if you want to penetrate a dense cloud, for example, well, all the particles below, for protons below 1 MeV and for electrons below 10 to 5 eV, will not enter because they will cool before entering the cloud. So you need something more sophisticated than these simple extrapolations. So what is the simplest model you can build? The simplest model you can build is to say, okay, I have my Voyager spectrum is still representative of the entire galaxy, but then when particles enter the cloud, I have to account for energy losses. To maximize ionization, I assume that particles inside molecular clouds go along straight lines. No, you cannot do better than this. You take Voyager at the edge of the cloud, and then particles enter along straight lines. If you do this, you get this blue curve. And this is a contribution from protons, and this from electrons. So you see that in a realistic and optimistic model for the cosmic ray ionization in clouds, you don't fit data. Because in diffuse clouds, you have a gap. Again, for dense clouds, maybe it works. Okay, now, how do we understand this? Is assuming a straight line propagation of particles realistic? No, because cosmic rays are charged and we have magnetic fields. So the optimistic scenario, it has problems, and probably these problems are underestimated, because in a realistic scenario, we should include the fact that cosmic rays are affected by magnetic fields. Now let's try to build a simple model to describe the penetration of cosmic rays inside clouds in a more realistic way. So let's do something brutal. This line here is the edge between the interstellar medium and the molecular cloud. And the magnetic field, we take, this is also not realistic, but we take a magnetic field which is just aligned along this direction. Now, outside of the cloud, we have the hot phase of the interstellar medium. Again, it's brutal, but it's important to understand the basic physics. So we have fully ionized gas. And in the fully ionized gas, you can develop magnetic turbulence easily. And so you expect cosmic rays to diffuse in this turbulence. Now, if you go inside molecular clouds, you have neutral gas. Molecular clouds are very close to neutrality. And in a neutral gas, you kill turbulence due to ion-neutral friction. You kill very effectively turbulence. And so we say that inside the cloud, cosmic rays go along straight lines. Now, let's take now, far away from the cloud, like at infinity, we take cosmic rays at some average galactic level. We take Voyager, okay? We assume that Voyager is representative for the entire galaxy, and we take it here. Now, what happens? It happens that inside of the cloud, the main difference is that the density is large, and so cosmic rays lose energy. So we expect, naively, to have less cosmic rays inside the cloud with respect to outside, because outside energy losses are much less important because the gas density is low. So if you have less cosmic rays in with respect to infinity, it means that you must have a gradient of cosmic rays between far away from the cloud and inside the cloud. And let's say that this gradient operates on a given length. A gradient in the distribution of particles means that you have anisotropy in the particle distribution. A naive way to see it is that if you have a flat distribution of particles, you can keep it because you have the same amount of particles going from left to right and right to left. So you don't change the gradient. But you have a spatial gradient, you have more particles going one direction than the other. So you have an anisotropy. An anisotropic distribution of particles in a magnetic field generate instabilities. And there is an instability called streaming instability, which does this. If you have more particles here than here, particles will flow into the cloud, because the anisotropy will push particles to enter the cloud. In this streaming of particles will amplify the background magnetic turbulence. So if you have alpha waves, the amplitude of these waves will be amplified. If you amplify the amplitude of waves, you increase the effect that they have on particles. So particles will scatter more effectively on these waves, okay? And this is a scenario which is more realistic because it takes into account the fact that you have magnetic fields. So basically, cosmic rays are here, then at some point, as the cloud is a sink for cosmic rays, you create this gradient, so particles flow into the cloud and they lose energy and they disappear, okay? Now, let's see what is the role of this streaming instability. So let's take the flux of particles at the edge here. In this XC is the edge of the cloud. What is the flux of particles entering the cloud? There will be two components. The first one is a diffusive component. So you have to imagine that in a turbulent magnetic field, cosmic rays diffuse. They don't go straight. They diffuse. They do complicated paths. This is a diffusion coefficient of particles, and the flux entering into the cloud is the diffusion coefficient times the gradient. You see that here the gradient enters. If you have a larger gradient, you have more flux because because cosmic rays flow faster down the gradient, okay? And if the diffusion coefficient is larger, the flux is larger because cosmic rays diffuse faster, okay? Then you have a second term here, which is an advective term. Alpha waves are amplified only waves that move in the same direction of cosmic rays, because cosmic rays transfer momentum to the waves, but if they flow in, it means that they only amplify waves getting in. And cosmic rays scatter onto waves, so they are kind of attached to waves. So if you have a net flux of alpha waves going from left to right, also cosmic rays will be advected from left to right. If you have waves moving in both directions, this term would be zero. But here you have only waves entering the cloud, which are amplified. Okay, so now let's do very sophisticated mathematics. This gradient, we say that it is the spectrum of cosmic rays at infinity minus the spectrum at the cloud divided this Lg, which we defined as the scale of this gradient, the spatial scale of this gradient, times the diffusion coefficient. And then this is VA, the alpha speed, times the density of cosmic rays at the edge of the cloud. Now, what is Lg? We don't know, but we can use dimensional analysis. It can depend only on these quantities of the alpha speed and of the diffusion coefficient of cosmic rays, because these are the only quantities determining the structure of our cosmic ray distribution. And so dimensionally, the only way to make a length is d over VA. Now, if you plug this in, magically, the diffusion coefficient simplifies, and you get that the flux of particles entering the cloud is VA times F at infinity, not at the edge of the cloud, okay? So this is the sum of the diffusive plus advective flux of cosmic rays at the edge of the cloud. And it's something a bit magic, but in fact it's not magic, it's physics, is the alpha speed times the flux of cosmic rays at infinity. And this flux can be determined independently on the effectiveness of streaming instability, because these are only quantities. VA depends on the ambient, on the background magnetic field, and F0 depends on infinity of quantities at infinity from the cloud. The scale of the gradient, this depends on the streaming instability. So if the streaming instability is more important or less important, this scale of the gradient changes. But it always compensates here. So this appears in the final solution, okay? An implicit assumption that we made here is that the scale of the gradient should be smaller than the magnetic field coherence length. Otherwise, of course, this doesn't work. So you have to imagine a magnetic field which has a reversal scale which is larger than the gradient. Otherwise, our boundary condition at infinity is wrong, okay? Very good. Let me skip this. So now that we understood the physics of the penetration of cosmic rays in molecular clouds, let's try to determine the spectrum of cosmic rays inside clouds. Again, you can take the transport equation and solve it, but there is a simple way to determine this in an almost analytic way. So the clouds has two sides, and you have this converging flux of cosmic rays and of alpha waves because of the fact that the cloud is a sink. So you have the flux of particles into the cloud is 2F0 VA. The 2 is because you have two sides of the cloud, and the magnetic field is aligned this. And then you have the cloud is a sink, so you have a flux down in momentum, which is due to P dot. P dot represents the loss in momentum due to ionization losses. So basically particles get in, and then they are dumped into the cloud due to losses. When these two fluxes are equal, how much you put in and how much you remove for energy losses, when these two fluxes are equal, you have steady state. And so you can simply equate these two fluxes and get spectra inside the cloud. Then, of course, you can do it in a more sophisticated way, solving the transport equation in space and time and whatever. And this is what we did here. But you can get a very good approximate solution just balancing fluxes. So here is the spectrum of cosmic rays for protons and electrons, and black is Voyager. So what we put as a boundary condition at infinity. Then the red line is the spectrum at the border of the cloud, and the green is the average spectrum in the cloud. So at very high energies, these three curves coincide. So at very high energy, particles move so fast that they can penetrate the cloud without losing energy. And so basically you have a flat distribution of cosmic rays in and outside of the cloud. So all these curves coincide. Then at some point you have a difference, and this difference kicks in when particles, it takes them more time to cross the cloud, and so they start to feel energy losses. And so at some point you have that the particles inside the cloud are less than the particles outside of the cloud. Now, the fact that the spectrum at the edge of the cloud coincides with the average spectrum in the cloud, it means that the distribution of cosmic rays in the cloud is more or less flat. The spatial distribution is flat. So how is it possible if cosmic rays lose energy entering the cloud? It is possible because take a cosmic ray here, it enters the cloud, and then let's say that in one crossing, the cosmic ray loses a very, very, very small fraction of the energy. Then it gets out of the cloud, but here it feels waves pushing him back. And so the cosmic ray does a lot of crossings, left to right, right to left, and so on. And so it loses energy, but in many, many crossings of the cloud. That's why the spatial distribution is flat, but the spectrum is suppressed. If you go to even lower energies, you see that the spectrum at the edge of the cloud becomes different from the average spectrum of cosmic rays, which means that you have a gradient of cosmic rays inside the cloud. And so this energy where this happens, it represents the energy below which cosmic rays lose energy in less than one crossing. So cosmic rays enter, lose energy, and die without getting out of the other side. Okay? Good. So now that we have measured, we have estimated the spectrum of cosmic rays inside the cloud, we compute the ionization rate. And here is the differential ionization rate, so is how much particle ionize per energy. Then if you integrate this curve, you get the total ionization rate. And so again, black is Voyager, and the color are the ionization rate inside clouds of different column density. And you see that this is very important because clouds act as a filter of low energy particles. You see that if you compare, so the peak of the differential ionization rate for both protons and electrons is always at around 100 MeV or something like that. So it means that the problem that we had with the fact that we didn't know where the electron ionization rate was peaking, if you do a realistic model of the penetration of cosmic rays, this problem disappears because these particles die. They are not longer inside the cloud. So what you need to know is the spectrum of cosmic rays in the MEV-GeV domain, which we know because Voyager measures it in MEV and other instruments in the GeV. Okay? Good. So now we know this. We started from the spectrum outside of the cloud. We computed the penetration in the cloud, and we measured and we estimated the spectrum inside the cloud. Let's compute the ionization rate now inside the cloud in a realistic model for the penetration. And again, we have a problem because now here are the data for the ionization rate, and the black line here is our prediction for protons plus electrons. And you see that there is a discrepancy by 1 to 2 orders of magnitude. So this is a problem because we observe ionization rates that are much larger than what we expect from the spectrum that we measure locally penetrated into a cloud. So let's go back to the distribution of cosmic rays in the galaxy. This, you remember, was a distribution in space of high energy cosmic rays. And this is a distribution in space of ionization rates. And you see that what you would expect from Voyager is this, 10 to minus 17, and we are here. What you observe in clouds far away from us is here. And what you observe in the galactic center, in clouds in the galactic center is here. Now, please note that the scale here, the scale here is logarithmic. So it means that Voyager is like 100 times below the intensity of cosmic rays in clouds, which is 100 times below the intensity of low energy cosmic rays in the galactic center. So we are not talking about factor of 2, we are talking about orders of magnitude. So there is really something we don't get, we don't understand, okay? While in the gamma ray, you see just variation of factor of 2, 3. So how do we solve this problem? The galactic center, I will ignore because we don't know yet. We have no idea, but we are working on it. Let's see how we can try to solve this discrepancy between what we observe locally at the Earth and what we observe in molecular clouds in the galaxy. So there are several possibilities. The first one is what we call the carrot. The carrot was something introduced a long time ago for a completely different problem. The carrot is this. This is the cosmic ray spectrum measured by Voyager. And then you say, this spectrum is still representative of the entire galaxy. But if you go to energy below the lowest energy data point, you get an extra component. This is the carrot. Basically, you have a kind of a peaked component just below the last data point of Voyager. You may think this is cheating, but well, this is not excluded by data. So why not? You put an extra component. And this is the thermal component of the interstellar view. So you have thermal, and then you have this carrot, and then you have Voyager. This scenario does not work for a simple reason. Again, energy losses. In this energy domain, so you have to be below MeV, so below this, the lost time of protons and electrons is very, very, very short. You need to cross a very small amount of matter to cool particles. So if you want to keep this everywhere in the galaxy, it costs a lot of energy, because if you inject these particles, they are immediately cooled due to ionization losses. And so you have to replenish the galaxy constantly at a very large rate. And we tested this, and you need an unreasonably large amount of energy. So this is disfavored on energetical grounds. Then you can propose another solution. You say, okay, we have cosmic ray sources inside clouds. So Voyager is nothing to do with Voyager, is nothing to do with the background of cosmic rays. You have cosmic ray sources inside clouds. And this may work because, for example, in molecular clouds, you form stars, and we know that protostellar jets can accelerate particles up to GeV with no problems. So you say, okay, I put the sources where I need the large ionization. But the problem is that of this scenario is that this works only in some situations, because some of the clouds from which we measure the ionization rate are starless cores, are very quiet molecular clouds where there is no star formation going on, nothing going on. So this may work only in some clouds, but not in all. So the problem still remains. Then there is another solution, which is my favorite because we proposed it, but then you can judge yourself if you like it or not. And the solution is the following: is related to the stochasticity of cosmic ray sources. So if sources of cosmic rays are supernova explosions, these explosions are stochastic in both space and time. So you can say that if you assume, the calculation that I presented before, where we computed this predicted ionization rate in molecular clouds, was based on the assumption that Voyager was representative of the entire galaxy. The spectrum that we see locally is the same everywhere. But if sources are stochastic, this is not necessarily the case, because if you are closer to a source or far away from a source, you can see something different. And now, what we did was to simulate the explosion of supernova in the galaxy and do many realizations. And for example, you can have, and here is, the cross is our location in the galaxy, these are the spiral arms, and the dots are our simulated supernova, recent supernova explosion. And you see, for example, you can have a situation where you have a very nearby source to us. And if this is the case, low energy particles can reach us without losing energy due to ionization, because the source is very close in both space and time. And so it could be that if you are very close to a source, the spectrum of your cosmic rays overshoots Voyager, because energy losses are not important because the source is close in space and time. You can have an opposite scenario where this, for example, where you see that sources are all far away. And so energy losses are very important, and you can have a situation where, in fact, if you are far away from sources, you get a spectrum which is below Voyager. if you sit at the right spot, you get Voyager. Okay, so with this stochasticity, it tells you that, and you see that this effect is important at low energies, not at high energy, because at high energy, particles don't lose energy through ionization. Okay, we can see this in another way. You can simulate the position of sources in the galaxy and then propagate the particles away from each source. And what you obtain is these shaded regions. So basically, the data points are AMS, and this is Voyager. And these red and light red region represent the 68 and 95 confidence level. So it means that if you take a random place in the galaxy, the spectrum will be within the red region 68% of the time, and within the light red region 65% of time. The solid black line is the median, not the mean, is important, the median of all these configurations. So it means that Voyager, you see that Voyager for protons and electrons sits nicely around the median and within the 68% bars. So it means that Voyager is something typical, but you may expect large fluctuations around this typical value. And as molecular clouds are most likely correlated with supernova remnant, because now molecular clouds, we form stars, and then stars disrupt molecular clouds and they explode as supernovae. And so you expect to have gas around the location of your supernova explosion. So now, if you take this dispersion, you can explain why the ionization rate you observe in some of the clouds are so large. And this is one possibility to explain this puzzle of the high ionization rate in clouds. Okay, now I think I am probably running out of time. How much time do I have?
I think, yes, you have a few more minutes.
Okay, that's
in order
fine.
to allow for questions as well.
Okay. Let me see if I can skip this. Probably. Okay. Let me skip this because we don't have time. And so let's conclude on low energy cosmic rays. So which are the open questions that we have on low energy cosmic rays? So the main issue is to understand the origin of these large ionization rates measured in clouds. And so the main question is, are the spectra of low energy cosmic rays measured in the local interstellar medium representative of the entire galaxy or not? Or we can reformulate this by saying, what is the spatial distribution of low energy cosmic rays in the galaxy? Why the atomic and molecular clouds have the same ionization rate over a quite large column density? This is another interesting question. Why is the ionization rate so large in the galactic center? Because this is gigantic ionization rate and we don't know. And then the other question is, what are the size of the acceleration of the low energy particles? Because, for example, some people suggested that there may be like protostellar jets, or even turbulence inside clouds could accelerate particle to MeV, and so this could explain the ionization. And then there is another question that I had no time to discuss, is the fact that we sit inside the local bubble. So we are not in the average ISM. So does this play an effect? And if this play an effect, probably I think it does for low energy cosmic rays, which are the more fragile, the more sensitive to local conditions. So now, the future. What can we do to know better the distribution of cosmic rays at low energy in the galaxy? First thing, this is now, because we can do it with JWST. When cosmic ray ionize H2, they produce, let's say, secondary electrons, and these electrons can interact with H2 and can excite H2. And there are some raw vibrational line emission in the infrared that can be seen by JWST. And this would be great, and I hope that we will get something very news on this from very soon on this from JWST, because there is no chemistry here. I mean, when you have chemical networks, you always have uncertainty related to how well you know your chemistry. But yes, there is no chemistry. You ionize, and the same electron excite H2. So this is a very clean channel to study cosmic ray ionization rate. Then you can go to X-rays, because when you ionize a cold gas, then when you have recombination, you produce the iron K alpha line at 6.4 keV. We have now some evidence of the presence of this line emission from a number of supernova remnants, which are likely source of cosmic rays, but these are we are really at the limit of what we can do with current instruments. So with instruments like Athena in the future, we will be able to measure the 6.4 keV line much better, and we will be able to trace better, again, low energy cosmic rays. Then another, this is even more important, I think, is MEV astronomy, because the interaction of low energy cosmic rays with matter can produce the excitation nuclear gamma ray line emission. So you bombard nuclei, you excite them, and then when they excite, they produce nuclear lines in the MEV domain. The MEV domain, as you know, is not covered at all. And so we badly need a new MEV mission, which possibly able to detect this nuclear emission from cosmic ray interaction with gas. And finally, radio, SKA. SKA is important because the synchrotron emission from low energy cosmic rays can be detected by this kind of instrument. And so I think that the combination of this observation in the future will help us in understanding better the low energy cosmic rays. Thanks a lot. I'm ready to answer questions.
Yes, thank you very much, Stefano. This was a very interesting and educative talk. And yes, we had also many students in the audience, so I hope they got the message that you wanted to give through this talk. So I think we have some time for questions. So if you would like, you can unmute yourselves and ask Stefano, or you can raise your hands. I'm just waiting to see if there are some hands raised. Okay, I don't see any hand raised, but I would like just to ask something in the meantime. So, Stefano, you mentioned about the ionization losses being very important for the low energy cosmic rays that penetrate the clouds. So I was wondering, is this amount of energy lost by the cosmic rays sufficient in order to disrupt the the astrogenesis in these types of molecular clouds, or is this an important factor or not?
No, it is important in the sense that the people that do star formation, they need to know the coupling between the gas and the magnetic field, because this determines, but this can affect the properties of turbulence and also the capacity of a cloud to collapse. And this is set by the ionization rate. So energetically, no, because MEV, I mean the bulk of the pressure is at GV, and GV is not very efficient in ionizing. You need to go to 100 MeV, 10 MeV, 1 MeV, and so it's I think that the distribution of GV particles in clouds is probably quite flat, which means that you don't have a gradient in pressure, so it's probably not enough to yeah, but it determines the coupling between magnetic field and gas. So
okay, that's important. And the values that are observed or inferred from the observations are within the ranges that people need in order to explain stellar collapse in molecular clouds, or is it far away? I don't have an idea. That's why I'm asking.
I think, okay, Okay, I think that the problem of star formation is, okay, I'm not a specialist of star formation, of course, but the problem of star formation is quite complex. And I think that in many works, people assume a ionization rate in their, and they deal with that. But for example, this quantity may change spatially, because next to the edge of the cloud and the center can be smaller, and so there are a lot of details that are not easily taken into account. I think that there are attempts to put this spatial dependence, for example, of the cosmic ionization rate in this simulation. But I mean, I'm not an expert of this, but I mean, the reason why this measurement of H3 plus were very important is that they showed that this is much larger than people expected. So people were using 10 to minus 17, which was what Spitzer computed like a century ago. And then until 10 years ago, they were using this. And then with this observation of H3 plus, it was realized that in fact it's 100 times larger. So this was important.
Okay, yes, thank you very much. I see one more question by Apostolos Mastichadis.
Yeah, hi, Stefano. Thank you very much for your talk. These open questions I have seen for many years from when I was a student. So, but I wanted to ask you, can we get any more information about these things from the cosmic ray positrons?
Cosmic ray positrons.
I remember the positrons have very different spectrum from electrons. So, what is the status of the field now in this respect?
So you want to use positrons to do what? I mean, for the low energy stuff? I'm not sure I understand.
I'm not sure if I have heard. Can you repeat, please? Can you hear me?
Yeah, I can hear you. No, I could hear the question, but I'm not sure I understood what you mean with. So with the positrons, you are talking about the low energy, or which energy are you have in mind?
Positrons that we have in cosmic rays. Electrons show this curve that you saw, that you have a peak and then goes down. But positrons, yes, if I remember correctly, look very much like protons in the spectral shape.
Yes.
So I was wondering whether there is some discussion in the field about what the positron, how the positrons are produced in all of this picture.
Yes. Okay.
And
so,
what the propagation is.
Yes. Yeah, this is indeed a thing that I don't understand much, because the positron, the antiproton, and the proton spectra looks very similar. And this, if you do zero order models, you don't expect it, because antiproton and positrons are secondaries of proton interactions, and so you would expect different spectra. So there were alternative models trying to explain this, but they really needed to radically change the entire picture, because you wanted to have basically a very fast escape time from the galaxy to keep all the spectra equal. But I think that at the moment, I think that, I mean, I haven't worked on that, but I think that at the moment people think that the fact that the spectra are all equal is kind of a coincidence. I mean, if you do models, you can obtain this, but there is nothing deep behind this having the spectra parallel. I think that this can be solved going to higher energies, to measuring better higher energy of positrons and antiprotons, because at some point, let me think, how was the point? If you go to high energy positron, at some point you should see energy losses kick in, so the spectrum should start to be different from the one of protons. And so I never worked in detail on this. It's something, honestly, something that I don't understand. It puzzles me that antiprotons, positrons, and protons are parallel, because so I don't have an answer, I think, to your question.
Okay, so I don't know, maybe we can like move to the next question, because there is one more.
Yeah, I was wondering whether the laws, I mean, how the...
We cannot hear you well. You are breaking up. Okay.
Yeah, I have my connection is rather poor.
Would you like to repeat your question, or you had a comment? Okay. So maybe we can move to the next question by Georgios Vasilopoulos.
Yeah, just a quick one. Thank you very much, Stefano. It's very educational for even those that are not very familiar with the field. So I have a question, since you mentioned the MEV missions, and this was something that we heard earlier today also, like there are no actual MEV missions. And I saw the spectra that you showed, that you even showed a lot of lines. So even if there is an MEV, is there something that is feasible, like in terms of detecting all these lines, or like an excess from all these lines? Is this something that the community has pushed forward, or there is any development on going forward in any kind of mission that can help, or is it like something that we wish for?
No. There are a lot of activities. Okay, there will be a small mission called COSI that will be launched soon, I think next year. This is a NASA mission, but it's a very small thing, so it won't see these lines. This we know already. You cannot see these lines. You can do other things, positron lines, but not this. Then there are Europe. In Europe, there was the e-astrogam mission that was proposed many times to ESA, but never went through. And on the US side, there was the AMEGO mission. And these missions have, I mean, in fact, this you see here is the sensitivity of the expected sensitivity of astrogam. So, and this is the emission of lines from integrated on all the galactic inner galaxy, basically. So this integrated emission is probably within reach of instruments like e-astrogam and AMEGO. The problem is that at the moment, none of this is funded. And I think that, I mean, there is a discussion in the community going on, and I think it's very unfortunate, because we don't have an MEV mission since COMPTEL, and it's a bit of a pity. And I hope there was something. Today, I mean, we had a seminar here in Paris, so we heard that in the US they are planning to repropose this in the next course, but at the moment there is nothing. So I think it is important to talk about this, to tell people that this is something very important, because we really need it badly. Even because, I mean, having nothing covering, I mean, it starts to be embarrassing, because if you, I don't have the plot here. Let me check it, maybe in the backup slide. But if you put all the sensitivities of all instruments in all energy domains, I mean, MEV there is a big hole, is something amazing. You have this big hole in your spectrum, and there are scientific motivation to do it, but to me, another motivation is the unknown. I mean, you have an energy domain where you don't know what's going on. So we may have many unexpected things. But for the moment, except for COSI, I mean, I know that there are also discussions in China to build an MEV instrument, and you know, Chinese people.
Maybe they will do it faster than.
Yeah, they go fast. So why not? But at the moment, there is nothing funded. I mean, that I'm aware of.
Okay, thanks. I was mainly worried about the energy resolution to get the lines, but yeah, I think you covered that. Thanks.
Can I also, since I don't see any other hands, of course, feel free to ask. If I don't see any other hands raised, I will ask one more question about your interpretation with the stochastic sources of cosmic rays. I'm not sure, is it true? I mean, do I understand it correctly that within your scenario, you would expect to find or to have recently within, I don't know how many years, thousands of years, near the molecular clouds where you find the higher ionization rates, to have nearby cosmic ray sources like supernova remnants? So is there such spatial correlation already evident?
Yeah, very good question. So let me show you. Probably you see it here. Okay. Here, these are the ionization rays from diffuse clouds. And you see that there are a lot of points and a lot of upper limits. So in fact, this is true. Thanks for your question, because it's something I should have discussed. We don't know how broad is the distribution of these ionization rates. So if ionization rates are all at this level, then your point is correct. If you want to explain them, you need a correlation between clouds and
sources,
which is not impossible to think, because I mean, everything correlates with matter, no? So if you have more matter. But if this is indeed very broad, then maybe that these are explained by clouds that by accident are next to sources, and these upper limit, if these guys are here, you don't need any excess. So it is interesting. I mean, it is a problem that we don't know how broad is this distribution, because at some point the flux is the line widths are too small and we cannot measure anymore. So we just have upper limits for this. These are H3 plus and OH plus. I mean, these are absorption lines. So yeah, it's a good question, but it depends. If the dispersion is small, you need a correlation. If the dispersion is big, maybe not. Okay,
I see. So at least for the denser clouds, where you have detections at different levels of the ionization rate, this does not mean that you need to have a cosmic ray source nearby the molecular cloud to explain that.
But yeah, no. But for large column densities, I think large column, because we have to think. Let me see the spectrum. No. Where did I do the spectrum of inside? Okay, here, for example, you see, if you, no, it's better this one. So it is a differential ionization rate, but more or less it reflects the spectrum of particles. So you see that if you increase the column density, the spectrum is suppressed at higher energies, but I mean, how do I? So for low column densities, you see that the suppressions are very dramatic, and then they start to go down more slowly. So because it is very difficult to suppress stuff here. So at some point, you can say that the high energy particles are penetrate, the low energy particles are completely cut away. But then you just have the tail, the cool spectrum coming from these particles here, and at some point these will become more or less stable, because high energy particles penetrate, and then you just have the cool spectrum. So I'm not surprised I'm not surprised by the fact that even the simple straight line propagation model works for dense clouds, because ionization could simply be the, I don't know, 10 GeV particles that enter, and then you have just the cool spectrum in. So I think for dense clouds, I'm less worried, honestly.
Okay. Yes, thank you very much for the explanation. If there are no other questions, I think we can thank our speaker, Stefano, because it has been already also too late for the audience. Okay, thanks, Stefano, a lot. And okay, we will resume our colloquia, I think, in 2 weeks from now. So check the website. Bye.
Bye-bye.